Our learning targets for today. Students will be able to perform similarity transformations. So that term right there, similarity transformations, is one of our key terms today. We'll take a look at that. Students will be able to describe similarity transformations. So when we say describe a similarity transformation, that just means that we can describe it. Students will be able to prove that figures are similar. We are not going to mess with proofs today. So don't worry about that one.
Not even think about it.
A similarity transformation, here's our definition, is a dilation or a composition of rigid motions and a dilation. So remember we had those things called a congruence transformation. And a congruence transformation just meant that we were moving a shape using a reflection or rotation or a translation. In the congruence transformations or in our rigid motions, the size of our what?
The slides aren't posted.
Alright, I'm not going to go do it right now. We got to keep moving. We have 13 minutes. In a rigid motion or in a congruence transformation, the size of our shape never changed. But now we're talking about a similarity transformation. Now a similarity transformation can include a dilation. So that means that our size will change. That's why it's similar, because it's still the same shape, just larger or smaller, but it's not congruent anymore. Do we see the difference there between a similarity transformation and a congruence transformation? That is a really good true-false test question. Do something with those two terms. Two geometric figures are similar figures. If and only if there's a similarity transformation that maps one onto the other. So again, we need to know the difference between similarity transformation and congruent. Congruent means we're not changing size. Congruent, we're just changing location. With a similarity transformation, we are changing size. So that means it includes a dilation. So like it says, two geometric figures are similar figures only if we can find a way to take this triangle and map it onto this triangle using those transformations that we've talked about. So that might mean that we have a translation to bring it over here, and then we have a dilation to make it larger. But similarity, there we go. Similarity transformation will always include a dilation. So here's an example. Graph ABC with vertices, all those, and its image after the similarity transformation. So first, I'll graph ABC. Now we are first doing the translation of plus 5 to the x's, plus 1 to the y's. So if we have A prime would be 1, 2, B prime would be 3, 3, and C prime would be 3, 2. Okay, so first we're applying that translation. So we're moving our triangle. 1, 2, A prime at 3, 2, B prime, and at 3. Oh, whoops, 3, 3. Following with me. We just did that first translation. What? We good? 215. Oh, well that's good. You got that? Oh, no, it's not. So first we apply that translation. Now we apply the dilation. So we're multiplying our x's by 2, y's by 2. So a double prime 1 times 2 is 2. 2 times 2 is 4. B double prime would be 6, 6. And C double prime would be 6, 4. So we have 2, 4 would be here. Way up here. And then we have 6. So in the white you can see I applied first a translation. We just moved our original triangle, and then we applied a dilation. So we're just combining some things that we've already done. And again, this whole action would be called a similarity transformation.
I don't even say transformation.
It starts out saying transformation.
What's the scribble at the end?
We're pretty quiet. Do we understand? We're just pulling together.
Yeah.
We're just pulling together what we talked about in the first half of this chapter with and adding a dilation to it. That's it. Sweet.
Yeah.
I'm glad you think so. So, now when we describe what transformation happens, this is where it can get a little bit tricky. If we're starting with the blue would be our pre-image, green is our image. How do you think we would go from the blue? Just name the transformations. You don't have to give me numbers. How would we go from the blue to the green? Reflect up across the Y. Yep. Then we have to use a dilation. Would our dilation be less than 1 or greater than 1? Would the scale factor for our dilation, would it be less than 1 or greater than 1? Less than 1, right? Because we're shrinking. Yeah. Yep. Perfect. So here's more specifically what that would look like. First, we're reflecting using the red, and then, just like Layla said, we would use a dilation. Now, if I did ask you specifically to give me the scale factor, you could look at like W. W is at 2, 1, and you could look at, you know that point P up here, or P prime, is supposed to dilate down to point W, right? We all good there? You're not trying to be on your phone, are you? Is that what I see? No?
No, it's pictures. I take pictures of the screen.
That's alright. But don't need to be doing anything else with the phone. How am I supposed to know what you're doing?
Can you look at the screen?
Well, that's not my job to look at your screen. It's your job to have your phone away. If we are looking at how we get from P prime down to W, we can just look at our X values. And what happened from this 6 to this 2? How do we multiply to get down there, or divide? Divide by 3, right? So we don't write our dilations in terms of division. We would write it in terms of multiplication, so we multiply by 1/3. So we can just choose, my point is, to find what we dilated by, we can just choose a point that we know is supposed to map on to another point and figure out what change happened there. You with me? I know you missed yesterday, but dilations are not too bad.
I've been through this before once.
Questions? All right. We have, I forgot I get to use both my screens. We have 2 practice problems.
No.
Start working on them, and then we'll finish them when you walk into class tomorrow. So, no. Yeah, yep, get started on them today. You'll finish them as your warm-up when you walk into class tomorrow, then we'll practice it. And we'll what? Who? Stop the recording? Yeah.
It's a little bit.